Am I audible now? Could somebody confirm?
Yes, sir.
Okay, thank you. V is a real vector space. Okay. And
So you're not sharing screen.
I'm not sharing screen. Okay. Now is it okay?
Yes, sir.
Yeah. Okay. There. Okay. So a bilinear form is a map, okay, from V cross V to R. Okay. Okay, so this is the equation for the map, such that, so it is bilinear, so it is linear on each factor, keeping the other factor fixed. Okay. Such that, so I'll just summarize this in one step. Yeah. So if you have AI, VI on one side and W from the second copy. So this is a when we write like this, unless there's something explicitly I say, I mean a finite sum. Okay, just okay. So a finite. So if you have a linear combination on the left, okay, so this function keeping the W fixed, this is linear on the first thing, so it will split. So I'm just rewriting what we did in a slightly different way from last time. Okay, and if you have something on the left, the first factor, and a linear combination on the second factor, then maybe just for again this is a finite sum, okay, and sum is over J. Okay. So this is true. Okay. Where the AIs and BJs are from R, so they are just linear combinations. Okay, and for all V and VI from V and sorry, W is also. For all AIs and BJs from R, and for all V, W, VIs and WJs in V. Okay. So that's why it's called bilinear. If you fix one factor, the function is linear on the other factor. And we also said that we can define on Rn, okay, this some vector x1 through xn, y1 through yn. We are going to define this, okay, as the function which says, so I'll just call this vector x and this vector y. Okay, x transpose a y, vector y, okay, where A is an n by n matrix. Okay. I mean, that is sort of clear from this. I mean, assuming it's a matrix, it is clear from this picture that S be n by n. Okay, is a bilinear form. On Rn.
So this is true for any bilinear form on Rn?
No, that is, yes, that is what we're going to prove now.
Oh,
That's where we start. I mean, we didn't prove it, but that's where we, it is while trying to state that I got, I used incorrect terminology and then confused myself with what's going on. Okay. So let me just, okay, so let us come to this, that exactly what you were asking. Okay. So, so we want to relate, I mean, this abstract definition to something concrete, matrix multiplication. Okay. So let V1 through Vn be a basis of V. Okay. So then, okay, let this be a bilinear form on V. So now we want to relate this to a matrix description like above. Okay. So let Aij be the result of this applying this bilinear form to this pair Vi comma Vj. So that's going to be a, we call this is going to be a real number. Okay. And let A be this matrix in which this is the ijth entry. Okay. So then, okay, so then proposition. Okay. So this is with notation as above. As above. Okay. Let V and W be inside V, with V equals A1 V1 A and Vn. So in other words, with respect to this basis, this vector V is given by the column vector A1 through A, okay, and W equals B1 V1 through B and Vn. Okay. So this is V and W are given by this. Okay. Then W is this matrix A1 through AN, okay, this matrix times, oh, maybe, sorry, maybe I should not have used A because I already used A to denote this thing. Let me call these things alpha. Alpha and beta just. Okay. So then you write the alpha, I mean, the column vector of alpha is what represents the vector V, but its transpose will be this row vector. Okay, matrix A, and then here beta 1 to beta. Okay. I mean, we what do we say? We ignore the difference between a 1-by-1 real matrix and a real number. Real numbers are identified with 1-by-1 real matrices or 1-by-1 real vectors. Okay. Or appropriately change to describe for complex. I mean, technically the right hand side is a matrix, a 1-by-1 matrix, but that is just think of it as a real number. Okay. So this is the proposition. Okay. It is relatively easy to prove. The question is to sort of to sort of come up with the A, but once we come up with the A, the proof is not very difficult at all. So what is VW? Okay. This is alpha I vi, beta I vi. Okay, maybe you should write beta j here now. Okay, this is I goes from 1 through n, j goes from 1 through n. Okay, now bilinearity, so keep the second factor fixed, okay, and just expand it with respect to the first factor. So we would get alpha I vi this. Now expand with respect to the second factor. So this is from I goes from 1 to n. Outside some j goes from 1 through n. Okay, vi vj alpha I beta j vi vj. Okay, maybe here it is convenient to write it here the side, and this, if you work it out, is exactly this right hand side. So in other words, every bilinear form is given by some, I mean, in coordinates, it's given by some matrix, some vector transpose times a matrix times this thing. Okay, so sorry, there was a question. Okay. So now let us ask what happens if we choose a different basis. Okay, so here we chose a basis. Here we chose a basis v1 through vn. Okay. What if we chose a different basis? Proposition. Okay, so this is 817 in Arden's book. I mean, okay, I probably won't face it exactly that way. I'm just saying this is what I'm referring to. Okay. So let the bilinear form on V. Let V1 through Vn and V prime 1 through V prime n be two bases of V. Okay. Let P be the matrix. Okay. Matrix for the change of basis. Okay. So what it means is, if you write down the vector, if you take any vector and you write down its coordinates with respect to the V basis, and you multiply by P, other way around. If you write down, so I want to phrase the other way around. Okay. So what does this mean? This means that if for every V inside V, if A1 through AN is the coordinate vector of V with respect to V1 through Vn, okay, and A prime 1 through A prime n is the coordinate vector of V with respect to V prime 1 through V prime n. So two different bases. What's the relation between these two things? Then P is such that, P is such, not that, not value. P has the following property. So this is an aside, just to clarify what we mean by. This is not. Okay, this is not part of the proposition. I'm just clarifying what we mean by matrix for change of coordinates. Okay. Okay. So with respect to the V basis, we have a coordinate vector. With respect to the V prime basis, we have another coordinate vector, and P has the property that A1 through AN is P times A prime 1 through A prime n. Okay, so this is what we mean by change of coordinates. Okay, and it is given by trying to express V prime in terms of V. V prime I in terms of the V basis and V prime and so on. Okay, that's how we get this matrix. Okay. Okay. So now, sorry, back to the proposition. Maybe the bit. Okay. Then, okay, maybe. Okay. So in the proposition, we have this P that change of basis. Okay. So let A and A prime be the matrix of this bilinear map. Okay. With respect to these bases. Okay. Then A prime is P transpose A P. It's not a similarity transformation. Similarity would be P inverse. So we're not saying A prime is similar to A, but A prime is P transpose AP. Okay. And just to clarify, okay, so this is a statement of the proposition. Let's go over it just once more. So we have given a bilinear form of V on V and two bases for V. Okay. And P is the matrix for change of basis. And the bilinear form is given by a matrix A with respect to the V basis. And so this is with respect to V. This is with respect to V prime. Okay. Then A prime is given like this. Okay. So this is the, okay. And what exactly, what exactly we mean by this? What property does P have? For all vectors V, if you take the coordinate vector for little v, if you take the coordinate vector with respect to the first basis and coordinate vector with respect to the second basis, then they are related by like this. And the P works for all vectors. That's what. Okay. Okay. So proof of the proposition.
Sir, what do you mean by the matrix of the bilinear form?
This one.
Oh, okay, sir.
Yeah. We observed earlier that any bilinear form is given by a multiplication like this, right?
Yes, sir.
When the x, here, any bilinear form is given by this, like this. Okay. So now, when we write like this, we want to avoid thinking about coordinates and just okay. Okay. So what is V? Okay. So let V be this vector let V be alpha I V I, which is also equal to alpha prime I V prime I. With respect to the two different bases, the coordinates are alpha i's and alpha prime i's, and W be the vector beta j V j, which is the other coordinates, it would just be beta prime j V j prime. Okay, so there are two vectors V and W whose bilinear product we need to take. Okay. But they are both expressed in the two different bases. So there are four expressions. Okay. So now VW is with respect to the first basis, it would just be alpha 1 through alpha n A beta 1 through beta n. Okay. This is the same as alpha 1 through alpha n is given by p times the corresponding primes. Okay, but we are transposing it here. So this would be alpha 1 prime through alpha n prime p transpose A, and here we'll have p beta 1 prime through beta n prime. Okay, but that's exactly the expression that we want for okay, so just let us just stare at the second line. Okay, what we want is the square matrix here. Okay, the square matrix here that has this property. V comma the bilinear product V comma W is the coordinate vector of V times a matrix times the coordinate vector of W. And that's exactly the expression that we want. So therefore, this is true for every V and W. So therefore, A prime is P transpose AP.
Sir, if that alpha into P into beta equal to alpha into P prime into beta, then does that imply that P equal to P prime?
No, say it again. No, there is no relation between alphas and betas.
No, I mean alpha 1 that considers that alpha 1 prime vector, like alpha vector and beta vector, then alpha vector into P into beta vector equal to alpha vector into P prime into beta vector. Does that imply that P equal to P prime? Like I'm trying to say that.
No, there is no P prime. I don't.
No, I'm just okay. So here alpha vector into P transpose AP into beta vector equal to that A prime, like alpha vector into A prime into beta vector. Does that imply that A prime equal to P transpose AP?
Yes, that's what it is. Yes, therefore, yeah, your question is this. I mean, does this thing that I marked in circle,
does this imply that
circle does it imply? Yes. Because
so that is unique, like is the middle thing.
So okay, no. Good question. Let us think about this. Suppose you have two matrices. Okay. Yeah, good question. Okay. This is uniquely determined. Okay, that's yes. So what exactly are we saying? We have two vectors. So now we can ignore that there is some coordinate-free description of the vector, etc. Right? So okay. Actually, good question. Sorry, this requires more work than. Just give me a minute. If if you have two matrices, sorry, I'm just okay. No, that is correct. Okay, so what do we have? So we have the following. Okay. For all vectors alpha 1 prime through alpha n prime and beta 1 prime through beta n prime inside Rn. Okay. Inside Rn. This expression. So let me just call this, okay, so alpha n prime up to alpha n prime, P transpose AP, beta 1 prime to beta n prime. Okay. This represents the bilinear form. Okay. And A prime also by definition represents the bilinear form. Right? Is this assertion clear? Means okay. Both represent.
Okay, so let's just, we can bring this in the left hand side, then take the use the distributive law, and then P transpose A P minus P A prime equal to, and this like the middle thing will, like this thing will
So
be 0 for all
just,
alpha. Yes,
correct. Give me a minute. Both represents the same bilinear form in the basis. Okay. I mean, the right hand side by definition of A prime, the left hand side by calculation. Okay. Yes. But what does this mean? I mean, okay. So now we want to conclude that these two, the square matrix is in the middle. I mean, P prime AP is equal to A prime. P prime AP is equal to A prime. But I mean, this thing holds for all vectors. Okay. So now just apply with 0, 1s, and 0 at the ith position. Okay. And P transpose AP and 0, and this is the jth position. So in other words, I'm saying put the ith transpose on the left side, take the transpose of the ith standard basis vector, and on the right side, take the jth standard basis vector. Okay. So this is equal to the same quantity. Okay. But what does this thing, what does this pick out? I mean, if you have a matrix and you multiply by a basis, standard basis vector on the left, transpose of that thing, and another standard basis vector on the right side, this is just the ijth entry of P transpose AP. And this is the ijth entry of A prime. And they are equal. That's what is being said. Therefore, P transpose AP equals A prime. Okay. Does this answer your question?
yes, sir.
Yeah. Okay. Yeah. No. Yeah. It's a. Yeah. The point is that this thing holds for all vectors. If it held only for some vectors, one would not have been able to argue. Okay. So that's what. Okay. So this one, this says if you change basis, okay, then what will happen? What happens to the bilinear form? Okay. So a corollary of this is that if P is an invertible matrix, then A and P transpose AP represent same bilinear form in the two different bases. I mean, okay, the bases that are connected by P, okay, these two will represent the same linear transformation, the same bilinear form. So, yeah.
So sorry, could you repeat the corollary? I didn't understand.
Oh, I was not going to write, but okay, now that you okay. Okay. So let B and B prime be two bases. Okay, and let P be the matrix for the change of basis. Okay. Then, so this is an invertible matrix P. Okay, let A represent bilinear form in with respect to the basis B. Then P transpose A P represents the same form with respect to B prime. Okay, so I mean, in other words, a matrix, I mean, two matrices A and P transpose AP, they represent the same bilinear form in two different bases. That's all I said. But this is the statement. Is it clear?
Yeah.
Okay. So this is so now some definitions. Okay. We say that a bilinear form is symmetric if for all VW inside V, VW is WV. Okay. Okay. And yeah. Yeah. Okay. So we'll when he says, okay, just a notational terminology, just to be clear, because Artin also uses this. When we say symmetric form, okay, this means symmetric bilinear form. Okay. Meaning we may not all the time say symmetric bilinear form, we might just say symmetric form. Okay. It is okay. Okay. So now proposition. How do we how do we identify symmetric bilinear form? So for example, okay, maybe we should. Okay. The dot product in Rn is symmetric. Okay. I mean, remember, dot product is this thing. If you have a vector x and a vector y, this is just x transpose y. Okay. This is dot product, and this is symmetric. Okay. This is a bilinear map, okay, and this is symmetric. Okay. In fact, we will see soon that. Yeah, I shouldn't. Sorry, there's not that. Okay, that's not. Okay, so now let's try to understand what symmetric forms look like.
This is the dot product with respect to like orthonormal basis, right?
Yeah. When we say dot product in Rn, we mean standard basis.
Yeah.
With no other, I mean, unless we quantify other things, we just mean when we say Rn, we mean with the standard basis and think of vectors as inside Rn. I mean, with respect to that basis, yeah. Okay. So now, proposition 1, let A be an n by n matrix. then the form, these are just vectors, okay, is symmetric if and only if A is a symmetric matrix. Okay. And second statement, a bilinear form is symmetric if and only if for every basis V, basis B of V, the matrix of the matrix of this form is symmetric. Okay, and in fact, if it holds, I mean, if it holds for one basis, it will also hold for every basis. We'll see. I mean, I'll clarify it in the proof. Okay, so let's prove these statements. The statement's clear. We want to understand when is a form, I mean, how to identify symmetric bilinear forms. Okay, in the first statement, we look at a specific bilinear form, which is the one given by matrices, some vector transpose matrix times vector. When is such a thing symmetric? When is such a bilinear form symmetric? And the proposition asserts that this happens if and only if the matrix is symmetric. Okay, and the second one, it says if you take an arbitrary bilinear form, that is symmetric if and only if the matrix, its matrix with respect to some basis is symmetric. Actually, what I wrote is at every basis, but we will see in the proof that it is for some basis. I mean, if you can prove for some basis, it will be true. Proof. Okay. So now, first, suppose a proof of one. Okay, and we are proving the if part. If A is a symmetric matrix, then the form is symmetric. Okay. So this is A is a symmetric matrix. Okay. So then if we take X transpose A Y, okay, so this is a 1/1 matrix. Okay, this is the same thing as X transpose A Y transpose, and this is the same as Y transpose A transpose X, which is because of symmetry of A, is the same thing as Y transpose AX. Okay, this is true for every X, and therefore the form is symmetric. Okay. So now, okay, this is just, I mean, all that is being used is that X transpose AY is a 1/1 matrix. Okay. So as I said, in this, when we discuss this, we will ignore the difference between 1/1 matrices and scalars. I mean, of course, in this context, we cannot multiply. We can multiply a scalar with a matrix, arbitrary matrix, but we cannot multiply a 1/1 matrix with an arbitrary matrix. Okay, but that is okay. So they're not. I mean, they're not logically the same, but although we wanted a function into R, right? what we really get is a function into what the set of 1 by 1 matrices over R. Okay, so this is just, so now only if,
Sir,
yeah,
so how did you go from A transpose to A in the last
and
step?
that is assumption. I mean,
Oh, okay, okay.
yeah. Okay, so now only if. So again, okay, so maybe it's a good idea to go back to this thing that we clarified last time, earlier. So here, how did we prove that these two matrices are the same? By checking their ijth entry. And how do we check the ijth entry? We take EI transpose times the matrix times EJ. Okay. So we do the same, that's what we did here. We do the same trick now. Only if. Okay. So if we take EI transpose A, EJ. Okay. So this, on the one hand, this is the ijth entry of A. This is, I mean, not on the one hand, this is always that case. Okay. On the other hand, by symmetry of the form, okay, EI. This is the symmetry of the form. I mean, symmetry of the form X transpose AY. Okay, so we can, and this is the JIth entry of A. And these are the same. Therefore, A transpose is equal to A. Okay. Okay. So this is the proof of one. Okay, that I mean the thing which says X transpose AY, that form is symmetric if and only if A is symmetric. Now, proof of two. Okay. Suppose that this is symmetric. So this I'm now proving the, which way did I state it? Linear is symmetric. So I prove the only if. Suppose this is symmetric. Okay. Let B be any basis of V. I mean, and V1 through Vn be any basis of V. Okay. So, but okay. So then the matrix of V with respect to this basis is given by the ijth entry of the matrix of V, matrix of the form with respect to B is, okay, this thing equals, okay, Vi Vj. Okay. This is Vj Vi. Okay. This is symmetry of the form. Okay. This is by symmetry. And this is the same thing. It says this is Jith entry of the matrix. Okay. So therefore, the matrix is similar. It is symmetric. Okay, this is an arbitrary B, so this holds. Okay, so this proves the only if part. Okay. And for the if, we actually need that it works for one basis. Okay. If. Okay. So let's.
So could you scroll up a bit?
Yeah. Enough? Further?
Yes, sir. So, okay, sir.
Yeah. Okay. If let B V1 through Vn be any basis, okay, in which is given by a symmetric matrix A. So then let V be alpha I Vi and W be beta J Vj. Okay. Then VW is this matrix. Beta n. Okay. Because the symmetry of A, this is the same thing as symmetric beta 1 through beta n, A alpha 1 through alpha n. Okay, this is sorry, this I'm sorry, I don't need to put a transpose here. I've already transposed it. Okay, so this is by symmetry of A. So we have this, but then the last quantity here is what we mean by WV. Okay, that is V is not V is symmetric. Okay, so this is how symmetric forms are. I mean, how they look like. Okay, they are given by the middle matrix is a symmetric matrix. Okay, so more about symmetric times it. Okay, more about. Let me just see how far I should go today. Okay, so I will just introduce these definitions and then I will probably stop. Yeah, some definitions. Definition. Let be a bilinear form, be a symmetric form, symmetric bilinear form on a vector space V, finite dimensional vector space, okay, a real vector space. Okay. Okay. We say that this form is positive definite okay, if this thing is greater than 0 for all non-zero vectors in V. Okay. Think of it like length, something. Think of like dot product. Okay. If you take dot product of a non-zero vector with itself, we get a positive number, which is the length of that vector, or square of the length. What is dot product? Square of the length of that vector. Okay, usual Euclidean length. So think of it like that. This is what that positive definite means. I mean the product with itself is positive. Okay? So this is what we have, and it is called positive semi-definite. Okay, if so, all these conditions are on the product with itself. I mean, the bilinear form being applied to the same vector. I mean, both copies are of the same vector. Okay, this is greater than or equal to 0. Okay, for all vectors or all non-zero vectors. Okay. Anyway, if we put in 0 by linearity, we would get this positive semi-definite. Similarly, we can talk about negative definite and negative semi-definite. Okay, so same condition. and negative semi-definite if this is less than or equal to 0. Okay, so then okay, so these are and indefinite if it's none of the above. Yeah. Okay. So, for example, dot product on Rn is positive definite. Okay. An example that has applications in physics, although I cannot explain what that, I mean, what it is the following, okay, which is what is called the Lorentz form, okay, on R4. It has to do with space and time and things like that that I do not know. Okay. So the form is given by so this, I mean, we will study symmetric forms and orthogonality, etc. later, I mean, more detail later. And we will see that this is sort of a, we can always think of them like this, but we'll come back to it later. Okay, given by the matrix. Okay, let's call this thing A. So that is X, Y. These are vectors inside Rn. This is just X transpose A Y. Okay. And if we throw in, if you put EI, EJ, EI, EI, so doing V comma V is what tells you whether it's definite or and I mean that sort of thing, semi-definite or definite or indefinite. Okay, so so in particular, if you just do this for EI, okay, this is 1 if 1 less than or equal to I less than or equal to 3, and -1 if I is equal to 4. Okay, just okay. So therefore, this form is indefinite. Okay.
Any indefinite form, can they induce, like, can they be just the inner product of the space?
So that is a good question. Any positive, any symmetric,
Any
positive
symmetric, any form, any
is,
definite form, like even if it is
yes,
negative, we can take the negative.
Yeah. So yeah, it has to be definite form. Yes, I mean it has to be a positive definite form. That will give, I mean, that will correspond to the dot product in some basis. Okay, but that requires, the proof of that statement requires some preliminary, I mean, some more work. So I'm going to postpone that. I mean, some part of it can be proved already from the stuff that we have discussed, but the key part of it will require some more work about orthogonal matrices, etc. So let me postpone that, the complete discussion of this question to later. Okay. Yes, but we will come back to this question. Huh?
Can you restate the formal statement? That is what implies this.
Yeah. So if we have a positive definite, if you have a, so similarly, so we can talk about matrices being positive definite. Okay, maybe I should just add that here. Let me just say it. So here we defined forms for being positive definite or semi-definite or indefinite. Okay. Similarly, we can say that an n by n matrix A is positive, definite, etc., etc. The same 5 things that we mentioned above. If the form X transpose AY is, X comma Y is X transpose AY is positive definite, etc. Corresponding. Okay. The same way we can define matrix to be. So then the question is, when does such a thing, X transpose AY, represent the dot product in some basis? Okay. That happens if and only if A is a symmetric positive definite matrix. Okay. So this is a theorem. Okay. So the proof of the statement, I want to postpone it till maybe next week or something. Just a little, not too far, but one needs to just discuss a little bit of stuff before that. Okay. So therefore, I just postpone that. Okay. But yeah, that's the statement. That this form X transpose AY gives the dot product with respect in some basis, if and only if A is a symmetric positive definite matrix. That's the precise statement. Does that answer your question?
Yes, sir. Thank you, sir.
Yeah. So we'll revisit this point, but some part of it can be proved, but I think it's better if we just. But the key part requires some work, so let us just postpone it till then. Okay, so maybe should I introduce? Sorry, I need to talk about Hermitian forms. Maybe I just define, but I'll do a recap next lecture at the beginning. Okay, Hermitian forms. Okay, so now V is a finite dimensional complex vector space. Okay. By a Hermitian form, okay, on V, we mean a map. Again, we will denote these angle brackets. To C such that. Okay. So here there is a slight difference, which is it is a complex conjugate on the first factor, and so it is conjugate linear on the first factor and linear on the second factor, such that. So I think depending. So I'm just following Artin's convention, but I think there are books where the other convention is used. Okay. So but let us not mix up too many things. So I just follow what Artin follows. I don't remember what Hoffman Kunz or something like that. Okay. Such that the following. Okay. So okay, some alpha I Vi and W. So this is the on the first factor. We are taking a linear combination of vectors from V. Okay. This is alpha I bar Vi W. Okay. So this is the first condition. Second condition is, okay, so this is what is called conjugate linear. On the first factor. So there is a complex conjugate here. Okay. Second one is linear on the second factor. Okay. And okay, so it is already similar. Similar, as an English word, not a mathematical word. Okay. Already shows some similarity to symmetric forms. But here it is what is called the Hermitian. So this is just linear in the second factor. Okay. What is called Hermitian symmetry. Okay. Which is V W. So if you transpose V and W, I mean not transpose. If you take this, swap their order, okay, V and W, this is, if it were a symmetric thing, okay, we would just write W comma V is same thing as V comma W. Okay? But this is what is called Hermitian symmetry. There's a complex conjugation here. Okay, so now you may ask, why is this complex conjugation introduced in these things? As you will, as you learn, as you go further, you will realize that a lot of definitions, are made after people have historically, after people have thought about various contexts in which similar calculations have to be done. And so, after a lot of consensus of, I think people will come up with some definition. Okay. For example, people had been thinking about groups from Galois time, which was late 18th century. But by the time groups were formally defined as, okay, we have not yet seen groups, but we'll soon see. Okay. Groups were formally defined as an algebraic object worth of study. It was probably either 1800s or early 1900s. Okay. So that's the thing. So people observe certain objects with similar behavior and then realize that, okay, it is worth consolidating this into a definition and studying. Okay. So that is the reason why some definitions may look strange, but it is because the applications that people have thought about that that these definitions have been made. Okay, so this is what okay, and just the standard Hermitian form on Cn. Is okay. This vector. So let us say we have alpha 1 through alpha n, beta 1 through beta n. This is alpha 1 bar, beta 1, etc., alpha n bar, beta n. Okay, and okay, so this is okay. So this we can think of this as so. Let us say this vector is x and this vector is y. So this is just x, okay, y. So this just means conjugate transpose. Okay. We have just conjugated the entries of the matrix. Here it's a vector and then transposed it. Okay. So this is what. Okay. Okay. And for example, okay. If you take the same vector, so for example, x transpose x is just, okay, it'll be alpha 1 bar alpha 1, alpha plus alpha 2 bar alpha, etc. So this is just going to be alpha I. So it is some notion of length, right? Because this is alpha, each alpha I is a complex number. So this alpha 1 bar times alpha 1 gives the square of the length. Then we're just taking the sum of those squares. So this is the square of the length of the vector, okay, with the usual Euclidean notion of length. Okay. So I'll stop here. We'll quickly recap this Hermitian forms and discuss Hermitian matrices, etc. Okay. And then after that, so this will probably take us one lecture. And in the next lecture, we will, not next, in the next lecture, we'll do Hermitian things. The lecture after that, we will go back to real forms and then talk about orthogonality. And then we will, and we'll see positive definite forms there again. I'll stop here.
Thank you, sir.